For those of you unfamiliar with Anton Paar, please let me take a few moments to introduce you to the company. Headquartered in Graz, Austria, Anton Paar was established in 1922 and has been known for its extraordinary precision machining for almost 100 years. In the mid-1900s, Anton Paar entered the world of scientific instruments by introducing a small angle X-ray scattering device. From that point, the company has grown to become one of the most respected manufacturers of high-quality scientific instruments in the world, employing more than 3,400 employees at 9 separate producing subsidiaries and 32 sales subsidiaries located around the globe. Along with another 50 distribution partners, Anton Paar delivers more than 170 distinct measurement solutions to customers in a wide range of manufacturing, research, and design-focused environments. In 2003, this family business was incorporated into the charitable Santner Foundation and has held a steady strategy of reinvestment into research and development efforts and manufacturing as many critical components in-house as we can, with the strength of the company always being its precision machining capabilities. In 2018, Anton Paar acquired Quantico Instruments, global leader for 50 years in the manufacture of instruments used to characterize porous materials. Speaking today will be myself, Francisco Sotomayor, your technical moderator, and I will also like to present to you our presenter, Dr. Martin Thomas. Today's presenter, Dr. Martin Thomas, is Anton Paar Quantitec's lead scientist. He graduated from the University of Birmingham in the UK with a master's degree in analytical chemistry, followed by a PhD in physical inorganic chemistry. His working career includes a period at Cookson Group, now Vesuvius PLC, as research investigator, followed by 6 years at ICI's Catalyst Research Center, now Johnson Matthey facility, as a principal research officer before joining Quantico Corporation, now Anton Paar Quantitec, in 1991. Dr. Thomas is co-author of Characterization of Porous Solids and Powders, Surface Area, Pore Size and Density, published by Springer, and is named co-inventor on 8 patents related to porous solids and their characterization. Today's webinar is titled Back to the Future, Carbon Capture and Storage. In today's espresso session, Dr. Thomas will be discussing how gas absorption measurements are used to characterize solids that have the potential to capture and store carbon dioxide. So now, I'm very pleased to introduce today's speaker, Dr. Martin Thomas.
Well, hello everybody and welcome, and thank you, Francisco, for that very nice introduction. As you indicated, today I'm going to be discussing carbon capture and storage. So specifically in this webinar, you'll learn how gas adsorption is used to determine the geometrical properties of microporous adsorbents that are currently used for or have potential for carbon capture and storage, and how to accurately determine CO2 storage capacity as a function of elevated pressure under various temperature conditions. So the areas that I'll discuss in particular are surface area, pore size and pore volume measurements by low pressure gas adsorption, the different adsorbents and calculations that we use for determining micropore size in particular, high pressure CO2 sorption capacity measurements, and something about surface excess, the property surface excess versus adsorbed amount. So coal and oil are nature's carbon reserves that have been tapped over centuries and burned for energy. So from black to gas, and that gas is carbon dioxide, of course. Now there's keen interest in capturing and storing that gas, carbon dioxide, 1, to prevent adding more of it to the atmosphere, and 2, keeping it on tap, perhaps as raw feedstock for various industrial processes. So this webinar will look at characterizing those functionally useful solids for capture and storage processes based on sorption. For some examples, I'll actually also be referring to methane, and methane, obviously another source of greenhouse carbon, is considered to be about 80 times worse than CO2, but its long-term global warming potential, GWP, is about 30 times that of CO2, because it actually has a shorter longevity in the atmosphere than does CO2, but still tremendously negative impact. Now, much CO2 currently is captured directly using liquid absorbers, alkaline and amine scrubbers, for example. but my focus here is on solid adsorbents. Now, these might include underground formations of rock, particularly shale, from which oil and gas might already have been extracted, coal, synthetic carbons such as activated carbon, and the youngest of the bunch of materials considered metal organic frameworks or MOFs. So it may seem obvious, but the best way to characterize an adsorbent is actually to carry out adsorption studies. Now, it's not the full picture, of course. For example, mercury intrusion porosimetry is a well-established method to evaluate the pore structure in geological formations. But in today's webinar, I will be restricting the methods and techniques to gas sorption. So, adsorption is the mechanism of capture, adsorption is the mechanism of storage, and adsorption is the mechanism gainfully employed in our technology and methodologies we use to characterize the functional solids of interest. And so using adsorption techniques, we can describe a porous medium in basically two ways. Firstly, what are the geometrical characteristics, the pore structure, if you like, in terms of pore volume, pore size, and area? And then we adapt our experimental conditions to understand the specific interactions between the target gas of interest, like CO2, as a function of maybe underground conditions or process conditions of temperature and pressure. Now, to be efficient, the candidate adsorbent phase should be able to efficiently capture and hold on to carbon dioxide. And micropores in particular, that is, pores of a molecular size that exhibit strong adsorption forces. And in this regard, micropores are generally favored. Now, the exact pore size, or more accurately, the pore size distribution, can also play a significant role in gas adsorption selectivity and the ability of a sorbent to separate, for example, CO2 from air or CO2 from methane. The preferred adsorption of a particular gas is also impacted by the specific adsorption enthalpy of the gas, which will also play into how easily the adsorbed gas can be recovered and the adsorbent regenerated. Now, of course, it goes to say that a desirable porous adsorbent should have sufficient volumetric capacity, and that's based on its porosity or pore volume, and to be, properly useful, it should have good kinetics, so it shouldn't be adsorbing so slowly. Now, before looking at the first set of measurements done, the structural characterization, and some examples of strength of adsorption, I want to spend just a few minutes considering what we mean by an isotherm, a low pressure gas adsorption isotherm, and what the isotherm means to us. So an adsorption isotherm is simply a data set representing how much gas or vapor is adsorbed as a function of increasing pressure at constant temperature. Now, these, what I call structure isotherms, that we gain by doing low pressure, low temperature adsorption, rely on physisorption forces. And so the pressure term that we use here is relative pressure, P over P0, where P0 is the saturation pressure of the gas. Now, I've presented here the basic types of isotherm shapes. And we'll see that for today's application, we're hoping to see mostly shape A, which according to IUPAC is called type 1. Maybe in some combination of what is labeled B here, what IUPAC called type 4. It's important to note that the absorption capacity of the analytical gas, as we see in these isotherms, may be more, maybe the same, or maybe less than the capacity for CO2 under CO2's working conditions. So these isotherms here do not necessarily directly represent the absorption capacity of CO2. These are used for the structural characterization of the pore structure, which is an important characteristic that we need to know in these adsorbent materials. Now, type 4 isotherms indicate the presence of mesopores, and they're really beneficial for kinetics. Though volume for volume, they have less pore surface area than do micropores. So in these adsorbent materials, micropores are very important, mesopores are important for kinetics and to increase the overall pore volume, that in order to take advantage of that, we might have to go to high pressures and in terms of getting CO2 to use those mesopore volumes. Now, these type 4 isotherms also have a characteristic of hysteresis between the adsorption and the desorption data. And the details in this hysteresis of mesopore containing solids can tell us a great deal about how the pores are interconnected, that is the pore network. So there are subtle details in these hysteresis shapes that tell us something about the pore connectivity. And we'll see some examples of that in a little while. Now, the gases that we use for structural characterization are usually nitrogen and argon at their respective boiling points. Now, these cryogenic conditions are required for the weak adsorption forces to be able to accumulate the adsorbate in the pores and on the surface. Otherwise, at room temperature, for example, the van der Waals forces involved are not strong enough to cause significant adsorption. We need the cryogenic temperatures. And we also use carbon dioxide at a very convenient ice water temperature. And we especially use carbon dioxide for studying carbons. And because of its small effective molecular size, it can wiggle into some micropores that are actually too small to admit nitrogen or argon, either absolutely or over a reasonable time frame because of the kinetics. The presence or absence of a quadrupole does, however, play a role as to whether the best choice is, for example, nitrogen or carbon dioxide or not. Quadrupoles in terms of physisorption pore size measurements are in fact a nuisance. So nitrogen is pretty much the standard way to measure surface area in mesopores, but its kinetics in absorbing into small micropores does limit its usefulness. And because of its quadrupole, we need a special pore size calculation called quenched solid density functional theory, QSDFT, that takes that interaction on carbons into account. This example shows nice type 1 isotherms on 3 different grades of activated carbon fibers, which are characteristic of micropore solids with no evidence of any measurable mesopores or small macropores. So a nice plateau on the isotherm, which is representative of total pore filling, from which we can deduce a geometric pore volume, at least the pore volume that can be filled by nitrogen molecules. Now, if we have a lack of quadrupole, as we have in argon, and a higher measurement temperature, as we have for argon at its own boiling point, means that micropores using argon at 87 Kelvin fill at a higher relative pressure than they do with nitrogen. And everything considered, this leads to faster kinetics, shorter measurement time, which is nice, and higher confidence in the pore size calculations, because that pesky quadrupole, which has nothing to do with the size of the pores in the solid, can't interfere in the calculations because that quadrupole is absent in argon. And also on this slide, we can see what changing the temperature by almost 200 degrees, moving towards carbon dioxide, can do to a physisorption isotherm. It shifts way up into much higher relative pressures. So we'll look at carbon dioxide next. So at these elevated temperatures, say 273 Kelvin, and a higher absolute pressure, because the P0 at this temperature is about 26,000 torr, CO2 can access micropores, which are maybe not accessible for nitrogen at 77 Kelvin or argon at 87 Kelvin. And in doing so, we experience a much faster analysis. And due to these higher diffusion rates into these very small micropores, equilibrium is achieved very much faster as compared to nitrogen absorption at 77 Kelvin. Which means a really dramatic decrease in analysis time. You know, maybe 5 hours for CO2 versus, you know, maybe a day, day and a half, sometimes 2 days for nitrogen for critically sized micropores. Now, when we're using CO2 at these high absolute pressures, now, when I say high absolute pressures, in a normal vacuum volumetric instrument, we only can achieve up to about 1 bar pressure, so a maximum P over P0 of 0.03. In a normal instrument, we don't go to 26,000 torr. But we can get micropore size measurements without using a high vacuum system or low pressure transducers. So if micropore is the focus, on carbons, we use CO2 on carbons, not in zeolites, for example, because the quadrupole interaction of CO2 in zeolites precludes basically pore size measurements. Now, because of the constraint in P over P0 that we have in using CO2 and the limit on the P over P0 value that we can go to, when we're using CO2 in carbons for the structural measurements, we can't actually achieve high enough pressures to do a BET surface area measurement or to fill mesopores. But for a fast micropore measurement on carbon, CO2 is absolutely ideal. Now, here's an example where different isotherms of different gases we use to get a complete picture of the total pore size distribution quickly. So the large micropores and mesopores by nitrogen or argon. Now remember, argon will always be faster in the micropore region, plus CO2 for the very smallest micropores, which can be done even faster, and the pore size distributions can then be combined for a total picture. Now, if you want to use a single gas for the continuous pore size distribution in a single analysis with a relatively rapid micropore size distribution, BET and mesopore size distributions, argon at 87 Kelvin is the single gas solution to do these measurements. So now we have an idea of which gases we might want to use. Let's look at some pore size calculation issues. Now, nitrogen, as we know, has its own problems, the quadrupole, but so does the surface of a carbon due to a heterogeneous surface energy distribution. And without taking that into account, so some details of the surface now, not just the gas. So in a similar way that, like not taking into account the quadrupole of nitrogen, if we don't take into account something about the nature of the carbon surface, we can't get an accurate pore size because that heterogeneity in the surface is adding its own characteristics to the isotherm and can be misinterpreted when it comes to calculating pore size. Now, density functional theory, DFT, is the preferred style of pore size calculations today. But even classical non-local DFT, NLDFT, suffers exactly this misinterpretation because of this surface heterogeneity and produces an artifact in the pore size distribution, which appears usually around 1 nanometer in pore diameter as a minimum or gap in the pore size distribution. But even more state-of-the-art than NLDFT is this quenched solid DFT, QSDFT, which properly accounts for the surface heterogeneity, thereby significantly improving the quality of the pore size results in microporous carbons. Now, carbons aren't the only materials that we want to consider today, and shales, so a geostore, are important type of material. So shales have a distinctive pore structure, which is reflected in the typical shape of a nitrogen or argon isotherm, and I have some examples here. And they're usually characterized by having H3 or H4 hysteresis. And remember, these hysteresis loops are present when we have a mesopore structure in the material. And that peculiar looking closure of the isotherm at a little over 0.4 relative pressure is due to a phenomenon called cavitation. And this is caused by the condensed gas in the mesopores only being able to desorb through micropore sized cavities at a pressure slightly over 0.4 relative pressure, which is related to the thermodynamic properties of the gas and not the size of either the mesopores or the micropores. This cavitation is one type of what we call pore blocking. So the gas which is condensed in mesopores, when we desorb by lowering the pressure, that gas cannot leave until it meets this pressure, which is a characteristic cavitation pressure for the gas being used. And thankfully, DFT calculations done on the adsorption data and not the desorption data is not impacted by this cavitation, and so will give a continuous micropore, mesopore size distribution. Now, traditionally, macroscopic pore size calculations, pore size models for mesopore calculations, like the so-called BJH calculation, generally uses the desorption branch of the isotherm, because the way that these macroscopic models work, the adsorption branch is shifted and it can overestimate the mesopore size. DFT doesn't have the problem of overestimating the pore size from the adsorption branch, and we can get then a mesopore size distribution by using DFT, which does not have the artifact which comes from the desorption branch of the isotherm. We never want to interpret these pore blocking phenomena in terms of mesopore size, and particularly when it's due to cavitation. But with DFT, we're absolutely on safe grounds for both micropore size distributions, including heterogeneous carbons, and in the mesopore range. And through the appropriate application of DFT, we can get a continuous micropore mesopore size distribution. Now, this cavitation step, which we don't use for pore size measurements, nevertheless does indicate useful pore structure information, as we saw it's characteristic of many shales. And then we can know then, for example, that fluids will move through this total pore structure into and out of some of the mesopores through some micropore restrictions. And this plays a significant role in kinetics. For example, we see this impact in our structural characterizations through these gas adsorption isotherms, and they will also be present during the sort of like functional usage of these types of materials. So as a short review of part one then, we see that the choice of adsorbent is important. And for shales, for example, a combination of, or preferably argon 87 at 87 Kelvin with CO2 at 273 Kelvin if necessary is recommended. State-of-the-art DFT methods like QSDFT for carbons or NLDFT for the other materials. These methods for pore size calculations replace the older legacy methods based on macroscopic assumptions like the BJH calculation. And some interpretation of this hysteresis loop does give information about the pore connectivity. So now it's time to look at how we make direct measurements of carbon dioxide, and some examples I'll give of methane storage capacity. So now we're looking at the specific gases of interest. So we're moving away from only looking at the structural characteristics, but how that pore structure is going to be used, as it were, to indicate or control how much storage capacity we have. So the problem with many novel materials is that they face challenges in proving their effectiveness under realistic application conditions of pressure and temperature for the specific gases of interest. So just to recap, while knowing the surface area, pore size, or pore volume as determined by simple probe molecules like nitrogen or argon is indeed very useful and essential for screening materials, for materials with large pore volume and micropores of a certain size, it's still only a simple geometric measure. But the actual adsorption capacity of the intended gas can be very different from those used for characterization, and certainly done under very different application conditions. And this adsorption capacity is based on more than simply the pore volume. So things like molecular size and accessibility plays a role, as do the different densities of the different gases, with a significant dependency on temperature. So how much gas can be stored in a porous material depends on the temperature of the absorbed gas and its own density compared to the density of nitrogen or argon, for example. So here we start to think about ambient or super ambient temperatures for the target gases, rather than the cryogenic conditions for the physisorption of argon and nitrogen. Now, That's not to say that low temperatures cannot be employed for the capture and storage of carbon dioxide and methane. In actual fact, they can be, but of course that brings an additional complexity to the use of these materials. But it should not rule out shifting temperature down for these adsorbents to shift the working pressure down as well. Because in any absorption process, the higher the temperature, the higher the pressure we have to go to achieve a similar pore filling process. So let's dive straight into something a little unusual and introduce a material that we haven't looked at so far, which is a MOF. So these exotic adsorption isotherms of flexible MOFs like this ELM11 carry a possible advantage for CO2 gas separation due to this what's called gating behavior that these flexible MOFs have, in which the pores only open up above a certain pressure and then close usually below a somewhat lower pressure. And it creates these unusual looking isotherms, as you can see here. Now, this type of behavior, if we compare now a temperature swing adsorption desorption process performed an ELM11 shown on the left here by doing two isotherms at two different temperatures, 273 and 298. And we compare that with similar isotherms done on an activated carbon fiber shown on the right. Here, the closed symbols represent the adsorption branch and the open symbols represent the desorption branch. So if, for example, CO2, we look at CO2 at a gas phase partial pressure of 40 kilopascals, is adsorbed onto ELM at 273, okay, up here on this part of the isotherm here, so we've got almost complete pore filling, and then later recovered by heating to 298, which corresponds to the green isotherm, you'd be down here, so you'd recover all of this CO2 by just shifting the temperature just a little way. So nearly all of the adsorbed CO2 is released when equilibrium is established at the 298. Now, if the same process is carried out using a rigid adsorbent like activated carbon at these temperatures, only 40% of the captured CO2 is desorbed. So it's this downshift here. So adsorb here and desorb down to here thermally. And full recovery of the CO2 adsorbed onto activated carbon fiber requires heating to a much higher temperature and thus a more costly expenditure of energy for recovery. Now, a similar result would be obtained using pressure swing adsorption. So if you go to 40 kilopascals, for example, at 273, and then drop the pressure to 20 kPa, okay, this causes the desorption. We get almost all of the CO2 back from the ELM11. But again, if we compare it directly with the activated carbon fiber, moving down from 40 kPa to 20 kPa, yeah, we get a little bit back, but by no means all of the potential CO2 that could be absorbed. And you can see here that even going to these pressures, we do not have complete micropore filling. So generally for CO2 on things like carbons at ambient or superambient temperatures, we're going to go to much higher pressures than these rather low pressures. So this type of adsorption in these flexible MOFs are low pressure applications, and on other materials like carbons and zeolites and shales, we're generally going to use higher pressures at ambient or superambient conditions. So here are some literature examples of methane adsorption on different coal and anthracite samples. So here's an example where I'm using methane to show this behavior. And on this scale, 5 megapascals is equal to 50 bar. So these are high pressure applications at 25 Celsius. And ranking of adsorbents like these different samples. So not every coal or anthracite is born equal, and they have different adsorption capacities. So when planning to use these materials and to know basically what the geo-store capacity is, we can do laboratory measurements at high pressure, measurements of the target gas to basically understand how these materials will behave underground. So important for calculating underground storage capacity. And of course, you can extract these materials and process them, and they might be being considered for scale up in an industrial or other environmental process above ground. So again, planning the chemical engineering, if you like, the engineering requires us to know and make these measurements so we can classify these materials properly. So this is an evaluation for capture and storage of carbon dioxide. Has been similarly evaluated from a number of activated carbons derived from different coals. So these have been heavily processed to create activated carbons out of these coals to develop more of the micropore structure. And the graphs on the right indicate that the amount of carbon dioxide absorbed shows increasing correlation with the micropore volume, that micropore volume as determined by nitrogen physisorption, at least at the high pressures. So if you like, the physical pore volume characterized by nitrogen physisorption, and then we can see that for these particular materials, the CO2 capacity does indeed correlate with the micropore volume as determined by nitrogen physisorption, which is really, really nice, of course. Now, at the low pressures, the amount doesn't vary significantly with pore volume, which suggesting that the higher the pressure, the more important the larger micropores become as well. So the lower pressure, we're using the smaller micropores. At the slightly higher pressures, we're using the larger micropores, which might not be unexpected because given what we know about the relationship between pressure and pore filling. So we get less pore filling at lower pressures, more pore filling at higher pressures, and smaller pores fill at low pressures and larger pores fill at higher pressures. But the ability to quantify how much carbon dioxide can be accommodated and not solely how much nitrogen can be accommodated is essential when designing a process to take advantage of this behavior. So this is where we're starting to tie together the structural information and the real working capacity, if you like, of these materials for absorbing CO2 and methane and indeed other gases that you might be considering. Now, at low enough temperatures and high enough pressures, it's possible to observe adsorption of carbon dioxide in the mesopores. Now, it's not something that we normally observe. So as I mentioned before, when we're doing the structural characterization of carbons with CO2 at 273, we don't get to fill the micropores. But we can do it if we have a low enough temperature and at super atmospheric pressures. We can get filling of mesopores. Now, in terms of CO2 capture and storage, this means like additional capacity that we can take advantage of if we can get our process conditions working in this pressure and temperature region, okay, which normally means shifting the temperature down. You know, we're not working at super ambient temperature conditions, but if we can have a process where we can shift the temperature down and shift the pressure high enough, we can get to C and employ this mesopore filling for higher capacity. So again, remember that the higher the temperature, the higher the pressure we need to go to in order to see complete pore filling. This is true for both mesopores and micropores. And if we're working at high enough temperatures, we won't actually see any mesopore filling. We're going to rely solely on the micropore filling. So these are important considerations, again, when we're designing for above ground process conditions. Now, using carbon dioxide as a shale fracturing fluid is proposed as an alternative to water fracturing. One of its advantages being that the enhanced recovery of methane, which is based on the competitive adsorption of CO2 and methane in shales. And we can see this by measuring isotherms, as shown here on the right, of the two gases, CO2 and CH4. And you can see a higher capacity for carbon dioxide than for methane. So when CO2 is injected, it will actively displace the methane and take its place in the shale pores. So this means that while methane gas is being recovered, it's replaced with CO2 in the shale, which is now, the shale is functioning as a geostore for the CO2. So it's a win-win application, if you like. Okay, so this is where CO2 sort of meets shales, as it were. Now, when it comes to looking at these high pressure measurements, we use what are called vacuum volumetric or manometric systems. These are used for both low pressure and high pressure analysis. However, unique challenges are presented for high pressure adsorption that are absent or insignificant or barely significant in low pressure subambient analyses. And these challenges are the gas compressibility or the non-ideal behavior of high pressure gases, and the difference between what we call the true adsorbed amount and something that's called surface excess. Now, when we look at non-ideality, the basic operating theory in vacuum volumetric systems requires keeping track of the number of molecules in the system. If we know it's the different volumes and the various temperatures of those volumes and the pressures, we can calculate how much gas we have from the ideal gas law, PV equals nRT. And this is the ideal gas law. But in reality, analysis gases aren't ideal because of interatomic and intermolecular interactions. But in gas adsorption measurements done at low pressures, as is done for surface area and pore size measurements, nitrogen at 77 Kelvin, argon at 87 Kelvin, this correction for non-ideality is actually typically very small. We do still use it, we don't ignore it. But we use a simple correction called a non-ideality factor alpha, and that's all that's needed. It's a small calculation, small correction. But when we go to higher pressures means that the density of the gas is very much higher. So we encounter much more interatomic and intermolecular interactions. And we need something a bit more sophisticated. So you can see here, for example, the behavior of the amount of gas in a certain volume as a function of pressure. So the CO2 deviation from ideal gas behavior, which is the black line there, means that at some certain sort of important pressure, the CO2 doesn't sort of densify on a linear range, but it gets increasingly more dense as the pressure goes up. We have to know what this relationship is and apply a good quality correction. There are different equations to do this, and these corrections we refer to as equations of state, and there are different ones there. And basically this then gives rise to this more complex correction factor, the gas compressibility factor, which we call Z, which is not as simple as alpha because it has a fairly complex dependency on pressure and temperature. So we need to use these relationships. So processing the experimental data with different equations of state, as shown here, does demonstrate how much the compressibility of carbon dioxide affects the calculation of adsorbed amounts. So here's an adsorption isotherm, and without employing the proper equation of state, we can get quite odd-looking and deviant isotherms. The correction that we normally use for is the Helmholtz correction. It's generally the best one that we use, and If we don't take into this account, then we can never calculate the true amount of gas in the manifold and the sample cell and cannot calculate how much has been absorbed. But thankfully, we do have a number of corrections that can be applied independently to the experimental data. Now, next, we're not done yet. We have to account for a further complication of high pressure adsorption, and that's the distinction between adsorbed amount and surface excess, which becomes significant at even higher pressures. So the isotherm we corrected up to 50 bar with the compressibility factor, but pushing the isotherm even higher, we see an even greater decrease then from the isotherm. Now, these isotherms that we measure, this raw isotherm is what is called the surface excess isotherm, the surface excess isotherm. And as we go to higher and higher pressures, we actually see a decrease in that. So even though we've corrected for the compressibility, the isotherm can still turn over. And this is also known as a Gibbs isotherm, which represents what is called surface excess. So let's just have a look at a little bit more on that. And again, this difference between adsorbed amount and the surface excess, how large is the deviation? Well, it depends on the gas and the pressure and the density of the gas phase. So what is it exactly? So let me just step back one stage. When we're doing adsorption at low pressures, let's say below 1 bar in a normal vacuum volumetric system for structural measurements, the difference between the adsorbed amount, which is the amount of gas in the adsorption space, and the surface excess is typically negligible. So when we use what are called void volume measurements. We have to know how much gas is in the void space of the sample cell. And to know how much is adsorbed, we subtract that from what has been dosed to the sample cell. Now, this so-called void volume actually includes a bit of what is going to be called the adsorption space, where the adsorption is going to take place. So when we subtract the void volume from these measurements, we're actually subtracting out some molecules which will be in the adsorption space. Now, at low pressures, the error is very, very small. Now, here it's sort of magnified here. So if there are 10 molecules in the adsorbed layer, in the adsorption space, and when we subtract the amount of gas in the void volume, we'll actually end up subtracting one of those molecules out. So instead of measuring 10 molecules being adsorbed, we will observe the isotherm, after subtraction of the void volume, will say that we have 9 molecules adsorbed. This 9 molecules is the surface excess. Okay, it's how much more is associated with the surface, i.e. in the adsorption space, than would be there if the gas was just in the unadsorbed gas phase. So, but when we go to high pressures, okay, we're going to end up with our sort of first stage isotherm that's presented, the experimental isotherm, after subtraction of the void volume. The surface excess isotherm is only the solid red balls here, because even though everything in the adsorption space is adsorbed, it is associated with the surface. It is filling the pore. When we subtract out the void volume of that adsorption space and the pore volumes, we end up subtracting all of the white molecules. So the dark red molecules is the surface excess, and the white molecules are what we've subtracted out. So what we need to do to know the true adsorbed amount in the adsorption space is add back in those white molecules that are in the adsorption space. So we have to know something about the adsorption space. How big is the adsorption space? And then we can get the true adsorption capacity for the particular porous solid. So since we typically know or can calculate the density of the bulk gas phase by our chosen equation of state, and if we know or can estimate the volume of the adsorbed layer, we can calculate how much gas is actually in the adsorbed layer. So we correct for it. Okay, so we know the true adsorbed amount by taking the excess amount and adding in the product of the density and the volume of the adsorption space. Now that adsorption space for microporous material, we can assume that most of the adsorption space is in the volume of the micropore. So if we know the micropore volume, how do we know the micropore volume? From our structural measurements, notwithstanding any uncertainty that we have about, for example, nitrogen pore space filling or argon pore space filling. And this is where, if we want to do micropore volumes by low temperature, low pressure carbon dioxide, then that's another good reason for doing that. But if we know the micropore volume, we can reasonably assume the volume of the adsorbed layer is the volume of the micropores, and so we can calculate the adsorbed amount by correcting for the volume of the micropores and adding that back in to the surface excess, which is the raw isotherm, to get the total adsorbed amount. So proper interpretation of high pressure pore filling data cannot be achieved without knowing the geometrical properties of the pore structure. So that's why we always do both, because if we just do a raw high pressure isotherm, we get the surface excess, and that will always be less than the true adsorbed amount. Of course, we want the true adsorbed amount. Now, alternatively, for materials that have meso or macro porosity, where the adsorbed space, the volume for the adsorption space is not so well defined, we can instead use the density of the adsorbed layer in our layer calculations. And here's an example where both types of conversion from surface excess to full adsorbed amounts have been used. So the, if you like, the micropore filling and the layer model have been used, and in the left-hand graph, there's almost perfect agreement in this example, which is on a what's called a SOC MOF. So again, to bring MOFs back into the story here. So the middle and the right, the center and the right-hand plot show the measured and surface excess, the measured surface excess and the calculated adsorbed amounts over a range of temperatures for carbon dioxide and methane respectively. And here you can see how much the adsorbed amount has been corrected for above and beyond the surface excess by taking into account the adsorption space for these materials for both CO2 and MOF. So again, this is the type of correction that we'd like to make. Now, before we end up, I just want to introduce one last concept that we can take advantage of by measuring multiple isotherms from different temperatures. If we have these different isotherms at different temperatures, we can set about to calculate the enthalpy of adsorption, which basically tells us how strongly adsorbed is the gas, and therefore how relatively easy or difficult it will be to desorb it, either intentionally or unintentionally. So with a few temperature degrees shift, is all that adsorbed gas going to come back off? Remember that flexible MOF, we didn't have to change the temperature that far to get all the CO2 back out. So how much thermostating are we going to need in a storage scenario? Or now, if the gas is very strongly adsorbed, how much higher temperature might we need to get the gas back out or to regenerate the adsorbent? So in designing our processes, this is important information to know, sort of engineering information. Now, the heat of adsorption calculation that we use requires comparing a given amount of gas adsorbed at different temperatures at their respective absolute pressures. So we want to know from these isotherms, for a constant amount of gas adsorbed, how the pressure of adsorption varies. So we have to measure these multiple isotherms first. So for each chosen amount of adsorption in this example, say 50 cc's per gram as one amount, and then 100 cc's per gram, and then 150 cc's per gram, and so on, we apply what is known as the Clausius-Clapeyron equation. And so it's a simple matter of finding the corresponding pressure for whatever selected fixed adsorb amount we want to calculate for as a function of temperature. So we take an amount and we find the pressure that corresponds to that amount from the isotherm as a function of these different temperature isotherms. And then we plot these values of log pressure versus the reciprocal of temperature. This is the so-called Arrhenius plot, whose slope is delta H, that's the enthalpy, over R, the gas constant. And so from the slope of this plot, we can get the isosteric enthalpy, and that's the value that we're looking for. And this process, so this represents then the adsorption enthalpy for one adsorbed amount. So this process of calculating H for each given amount is repeated for a reasonable number of adsorbed amounts. And so the next step is to plot all of these calculated values of delta H against the corresponding values of adsorbed amounts. And then we get an enthalpy plot, which is how the heat varies as a function of the adsorbed amount. And depending on the gas, for example, or a different pore structure, the isosteric heat might be remarkably constant, homogeneous as a function of the adsorbed amount, depending on how narrow the pore size distribution is, how broad the pore size distribution is, whether there's any influence of different chemistry. You know, if we have a heterogeneous surface, so there are some strongly adsorbing sites and some more weakly adsorbing sites, we expect that the strongly adsorbing sites will be adsorbed to first with a higher enthalpy. So at lower coverage, we might expect a higher adsorption enthalpy. And then as the surface is more and more covered, or the pores are more and more filled, we might anticipate that the adsorption enthalpy will decline. But this is all important engineering information when designing a process to employ any of these materials of interest. And so in review then, our interest in high pressure gas adsorption measurements is to research and develop the adsorbent, particular adsorbent materials and processes for various industrial and environmentally useful applications. These adsorbents aren't just used for the environmental application, but in other sort of direct industrial chemical applications. And the goal of using high pressure measurements is to quantitatively determine adsorption capacity as a function of pressure and temperature. And in certain novel materials like the MOFs, it might not actually be very high pressure gas absorption measurements at all, taking advantage of rather interesting pore filling mechanisms. So just to sum up completely then, what we've looked at today, low pressure gas adsorption to understand the geometrical properties of our porous adsorbents using nitrogen, argon or carbon dioxide itself, and we looked at some examples, the common examples, activated carbons, shales, and MOFs, and high pressure adsorption measurements to measure working capacity, if you like, as a function of temperature, pressure, and to know the enthalpy of those processes. And we saw some examples of carbons, coals, and for CO2 and methane. So thank you very much for your interest and attention, and I'm happy to take any questions you have at this time.
Thank you very much, Martin, for that very interesting conversation. We had quite a few number of questions come in during the course of your presentation. So
right.
If you do not get your question answered by the end of our session, I will remind everyone that you can reach out to our support teams, Anton Par representatives, for answers to the questions if I don't happen to get to them by the end of our time here. So with that, I'll jump right into it, Martin. So
yep.
Early on in the presentation, we talked about interpretation of hysteresis, usage of DFT and stuff like that. We had a question regarding, those are sort of qualitative interpretations of hysteresis. What sort of calculations can you use, or how can you use calculations to sort of assist in the interpretation of hysteresis? Can you use different methods, right?
Right. Yeah. It is true that the hysteresis is a qualitative description. The IUPAC in their sort of guidance paper do a pretty good job of explaining what each specific hysteresis shape means. But above and beyond that, what we can know from basically the height of the cavitation step, that pore blocking step, that represents then the volume of mesopores or small macropores that are subject to the blocking phenomenon. So in the example I gave, there was some desorption of the mesopores occurring, albeit with some hysteresis, and that's normal hysteresis. There is a shift just due to the mechanism of mesopore filling and emptying, due to the slightly different mechanisms. Adsorption is a delayed phenomenon that has to overcome a nucleation barrier before you get mesopore filling, and then it empties from a meniscus, and it's more equal to the equilibrium state. So that's like normal hysteresis. So there's some emptying of the mesopores, but the cavitation step, then we can basically determine how much of the mesopore space is affected by this mesopore blocking. Now, if we want to investigate that hysteresis loop further, what we can do is what's called hysteresis scanning. So we do partial adsorption, partial desorption in and around that hysteresis region. I don't have any examples today because of time, but if anybody's interested in this, then please ask more about hysteresis scanning. So we can look in and around that hysteresis loop to know whether that cavitation step is sort of like constant, or it varies with which sizes of mesopores have actually been filled or not. So how the hysteresis changes as a function of how much of the mesopore space has been filled is that extra dimensional information that we can know about connectivity of the pore space. So that's the additional information that we would use to know that. Now, if anybody's into modeling of a pore space, there's sort of complex advanced modeling that one can do in the computer to say, well, I'm going to create certain pore structures in the computer and then do the calculations on the adsorption desorption process until you can mimic that pore structure. So basically it's like building up artificial pore structures in the computer to model the experimental data, but that takes some heavy lifting computing power to do that, but there are some groups who do that.
Thank you, Martin.
Yeah.
Moving to a little bit different part of the presentation, we saw some usage of CO2 for analysis of micropores.
Yeah.
And then we also saw later on in the presentation high pressure isotherms of CO2 looking at mesopore filling. So we had a question regarding whether you can use CO2 for calculation of pore sizes in the larger pore size range, and whether there are any calculation methods to do that.
Yes. There's a very important paper recently published about using the pressures of CO2 that can fill mesopores. Now, CO2 is a little bit difficult to work with. As you know, it doesn't go through a normal sort of condensation to liquid phase. So we have to be a little bit careful about how we do these measurements and how we calculate out the calculations. But there is a new calculation, and again, this comes from computer modeling of the behavior of CO2 in mesopores at these temperatures to do that. So it is just becoming available. So this is cutting edge CO2 measurement of micro and mesopore size to do that. So it's very exciting work. It's basically still in the very early phase of that. And obviously it needs some specific conditions of temperature and pressure. It's not something that we can do on our normal subatmospheric instruments. We have to go to superatmospheric pressures at reasonable temperatures in order to see the phenomenon. But that has been demonstrated for pore size calculation of mesopores. So basically, let's watch this space, and perhaps in the future we can have a presentation on that and give some more of the details. But if anybody's interested in that, do let us know, and the paper was linked in the presentation, and we can forward that link out back to you again. But yes, it can be done.
Thank you, Martin. I think we have a number more questions, but I think I'm going to wrap it up with just one more.
Right. Yeah.
Here, we had a student here who has noticed that they primarily use nitrogen for analysis of all of their samples, and you mentioned quite a number of adsorptives in your presentation. And so they were wondering about, is there recommendations to change their analysis gas for the samples, or how they should approach that question within analysis gas?
Well, the universal gas that we try to use these days is argon at 87 Kelvin, especially when you're doing microporous materials. If you're just doing mesoporous materials, nitrogen at 77 Kelvin is perfectly adequate for most materials. The quadrupole becomes less important, because when we're filling mesopores, the surface is already covered by an adsorbed film, so it's sort of insulating the surface from the quadrupole of nitrogen. But when you're looking at micropores, nitrogen is generally slow. It is a little bit more problematical when we're looking at all materials, because the quadrupole, it tends to be slow. You know, it's very slow in zeolite micropores. It's fairly slow in MOFs and carbons. We get a lot of speed advantage from argon, and we get, if you like, greater confidence in our pore size distributions, because as good as our DFTs are, argon, because of the lack of quadrupole, is basically easier to model, so our confidence increases in argon. Experimentally, it's hugely beneficial in terms of time, you know, for sample throughput and so on. So what some people we find do will screen materials using nitrogen on one instrument that maybe doesn't have the low pressure capability to get your BETs and pore volumes that way. And then the micropore size distribution using argon on you know, good candidate materials, or they'll do nitrogen plus CO2. But having said that, the universal gas, as it were, is argon at 87 Kelvin, because you can do a continuous micropore through mesopore through small macropore measurement in a single analysis.
Thank you, Martin. With that, we are just about out of time. So I'd like to thank everyone for participating in this webinar series. There will be another showing of this webinar at 4 p.m. Of course, as I mentioned previously, if we did not get to your question, which I did see there were quite a few, please reach out to us. We'd be happy to answer your questions.
Thank you very much, Francisco, and thank you everybody for watching, and goodbye, and please stay safe. Bye-bye.